Okay, welcome everyone to the MECH 314 lecture series, work from home, study from home due to the current health situation in the world. Last time, we are still on chapter 4. Last time we have derived the equations of motion for a fluid flow in differential format, which we call the Naiver Stokes equation, and these consist of the three linear momentum conservation equations, as well as continuity. And what we have done last time is we've written also the shorthand vector notation of the Naiver Stokes equation. And to remind you, we call this the capital D by capital dt of the velocity field is the total derivative of the velocity field is equal to, has two components, the local derivative d by partial t of the velocity, as well as the convective derivative, which is the del dot v operating on the velocity field. So the acceleration on the left-hand side is equal to the forces per unit mass on the right-hand side, which are gravity, pressure gradient, as well as viscous stress forces on our control volume. And the continuity or mass conservation equation, we wrote it as the divergence, the del, the divergence of the velocity vector field, and that's a dot product. So let's talk about continuity now and see what properties it has. Let's try to make sense of it. This is our continuity equation, as you have seen, and we wrote it as the divergence of the velocity field, where the divergence, the del operator acts on the velocity vector, and you do a dot product, and that's what you get over here, which we did the previous time. So let's see what this actually means. Let's take this cube, and it's infinitely long into the page, so it's uniform width into the page. There is no variation into the page. It's a two-dimensional flow field where the flow comes in from the left and leaves from the right, as well as it comes from the bottom at velocity v1 and leaves from the top at velocity v2. Now, let's look. This is a two-dimensional flow, so the third component, there is no flow in the z direction, and there is no variation of the flow in the z direction. So w is 0 and z is 0. So we write the continuity equation to be partial u by partial x plus partial v by partial y is 0. And then the del, or the partial, is just a delta. So delta u over delta x, we can approximate it as delta u as divided by delta x, and delta v divided by delta y, which, if you do delta u, is u2 minus u1 for our cube over here, divided by x2 minus x1 plus v2 minus v1 divided by the delta y is equal to 0. So what does that mean? Let's take the case where my flow accelerates in the x direction. So if I have my velocity u1 coming at 5 meters per second and leaving at 6 meters per second, it means that there must be some mass flow rate diverted from the v to go in here to feed into it. So if u2 is minus u1 is positive, then that means for my equation to be equal to 0, that my y component of the velocities, the delta v over delta y, has to be negative. If that's positive, that has to be negative. So if my flow accelerates in the x direction, my flow has to decelerate in the y direction, which means v2 must be less than v1. If my flow is divergence free and it's a constant density type of flow. So, but now let's look at the situation. So that's what it means to have a divergence free flow. It's constant density, it's incompressible, and that's what it means. It's incompressible. There is no accumulation of mass inside, no compression of the mass inside the control volume, such as the one that we have shown over here. But let's look at a compressible flow. What happens when we have a compressible flow? And an example of that is flow around supersonic jets. So here, this is a NASA photograph. You have a jet, an airplane that is flying at high speed, close or exceeding to the speed of sound. And what you'd see is a refraction type photography. What we see is that the air that is close to the tip gets compressed, and we get those shock waves. And a shock wave is just a fluid of increasing density. It's a rise in pressure. That's what a shock is. A rise in pressure means also a rise in density, as you can remember from your ideal gas law. And we see multiple shocks that come out that surround this aircraft. So we just mentioned the word speed of sound, and somehow that actually has got to do with the compressibility. So we define in engineering and fluid mechanics and aerodynamics an incompressible flow to have a Mach number squared to be less than 0.1. And many of you have heard of the Mach number, but if you haven't, Mach number is equal to the velocity of, for instance, for this jet, is the velocity of the jet divided by the speed of sound. So when your Mach number is close to 1, that means you're flying close to the speed of sound. And if compressibility effects, when does my divergence-free flow cease to exist? That's when my Mach number square is much larger than 0.1. So we mentioned the speed of sound, and we will talk about that a little bit more. But before we do, in terms of physics, let's try and see how we compute the speed of sound. For ideal gas, there is actually a formula for the speed of sound, and it's the specific heat ratio at constant pressure divided by the specific heat ratio at constant volume multiplied by the gas constant and the temperature in Kelvin. So for air, the Cp is 1 kilojoule per kilogram Kelvin. The CV is 0.7, so all this ratio is 1.4. The R is 287 joule per kilogram Kelvin, and the temperature is sea level temperature, room temperature, 25 degrees C, which is 298 Kelvin. So if you plug those numbers in here for air, you're going to get a speed of sound at sea level conditions of approximately 350 meters per second, which is slightly above 1,000 kilometers per hour. So that's the speed of sound that we are familiar with. For liquid, there isn't a formula to predict the speed of sound. Different liquids and solids have different speeds of sound, and they don't follow an exact formula. So for water, the speed of sound in water is actually much faster than the gas, and it's around 1.5 kilometers per second. So that's about 60 times faster, well, let's see, 1,500 meters per second compared to 350 meters per second. So that's maybe 5 times faster, the speed of sound in water than it is in air. So let's go back to talking about what happened. Why does my compressibility effects, why does my density not stay constant when the speed of the flow becomes faster than a certain limit, which in this case is Mach number square 0.1? And why does the speed of sound has got to do with it? Well, let's see what happens. Remember, let's go back to our chapter 3, when we looked at the Bernoulli equation. We had a jet coming out of a nozzle, and then we had a pitot tube. If you remember that, please go back and refresh your memory on this example. It's in one of the videos that we have on Moodle. And we call this point right here, because in the pitot tube, it's a measurement device, the water is stagnant. So this we call the stagnation point, and it has a stagnation pressure equal to the rho GH. Same thing if you have the air, so this is your jet, and relative to someone sitting on the jet, the air is coming and hitting the front of the nose of this aircraft. What you'll get is also a stagnation point right at the nose of the aircraft, and that's where the shockwave originates. And the stagnation pressure, if you go back to this example, has got to do with the density of the fluid far away from the shockwave multiplied by v squared. So let's see what pressure do we get, what stagnation pressure do we get if, let's say, I exceed my Mach number square of 0.1. So if you take the square root of Mach square 0.1, that means Mach of 0.31. And we computed the speed of sound to be 350 meters per second here. So let's multiply 0.31 by 350. So we're saying if my speed, my aircraft speed, right, exceeds 110 meters per second, so that's my aircraft Mach number goes, Mach square goes above 0.1, then I'm going to get compressibility effect. So let's take a close value, a slightly larger value than 110 meters per second. So let's take 130 meters per second. Let's say my aircraft is moving at 130 meters per second. And if there are some vehicles on the ground that do this, 130 is around 300 to 400 kilometers per hour. So this has been achieved on the surface of the Earth. But if we try to compute the stagnation pressure, plug in half the density of air, 1.23, and v square is 130 square. What you're going to get is a stagnation pressure at the nose of this fast aircraft, or this car that moves at 400 kilometers per hour. You're going to get a stagnation pressure of 10 kilopascal. You compare that to the atmospheric pressure of 100 kilopascal, that's 10%. And 10% is a magic number that we have in engineering, which says things become important if they start exceeding 10% of a certain value. So that's where all this story comes in. So now you can see why the speed of sound, or where the speed of sound gets in. But we didn't really talk about really what are the physics behind it. We looked at it in terms of Bernoulli, but that doesn't explain much. So in terms of physics of the speed of sound, let's take a pause now, and you look at the speaker of your computer where you can hear me from, and what you will the reason why you can actually hear my voice is that the speaker in your computer actually vibrates, and as it vibrates the air around it, and then it travels in the air. I am assuming that you're all living in an air atmosphere right now as you listen to me, and it hits your eardrums, and it actuates your eardrums to vibrate, and then the signal gets to your brain so you can hear me. That process for the information, that's my sound, to travel from the speaker of your computer to your eardrums happens at the speed of sound. So now we have now looked at the speed of sound as a quantity that measures the travel of information inside a fluid. That's how fast information travels inside a fluid, at the speed of sound. And that one example of this information is exactly my voice that you can hear right now, or actually the vibrations of the speaker on your computer. So now what happens if this airplane is moving faster than the speed of sound? Let's take it when it's moving slower than the speed of sound. Imagine a fluid particle that is ahead of the airplane, upstream of the airplane. That fluid particle will know that the airplane is coming because it senses the pressure waves coming from the nose of the airplane. And if that information gets from the nose of the airplane to where the particle is sitting at a speed, well, that information will actually move at the speed of sound. But now, if my airplane is moving less than the speed of sound, then the particle will have enough time to move out of the way, so it will deflect around the airplane. So it would have time to move out of the way and go in the streamlined type of flow. But what happens is when your aircraft is moving faster than the speed of sound, the information from the nose of the aircraft, the pressure information from the nose of the aircraft to where the particle is sitting, doesn't get in time. So the particle actually gets hit by this car, gets hit by this aircraft, and it wouldn't know that it's coming until after it actually has hit it. So this particle and this particle and this particle don't move out of place. So they actually accumulate at the tip, and that's what we call a shockwave. It's an increase in density. Just the air gets compressed, and that shockwave is just a compressive type of wave. Its properties include an increase in pressure as well as increase in density, and also temperature if you follow the ideal gas law. So that's really where the speed of sound comes into the equation. And that's really about continuity and about divergence-free flow. So when you have shock waves, the flow is not divergence-free, and this equation doesn't apply. For a compressible flow, mass conservation has a different format. It's similar. It has similar quantities, but has extra things to account for the compressibility effect. In this course, we're sticking with incompressible flow, where our assumption is that Mach number is less than 0.31. We mentioned the word of 2D flow over here, so let's now talk a little bit about 1D, 2D, and 3D flows. So in a 1D flow, the flow would be independent of the other two variables. So if I have a 1D flow in the z direction, the velocity will be independent of x and y. And if my flow is one-dimensional in the y direction, it will be independent of x and z. So it's independent of the other two variables and only dependent on that particular variable we're looking at. So this is an example of a one-dimensional flow in the z direction. If you look at a 2D flow, just like we looked at before, we have our two variables x and y, and it could be that the velocity in the u direction varies according to some function of y. But when we are two-dimensional flow, we can rest assured that if this has a width into the page, then if I take it at the plane of my computer, and then I go on my computer screen, and then you take the velocity distribution at 1 meter behind your computer screen and 1 meter in front of your computer screen, you'll see that there is no variation with z. So it's independent of z, where z is the perpendicular distance to your monitor. So when we're talking about a 2D flow, we're really thinking about the third dimension, that there is no dependence on that third dimension that doesn't show up in our picture. And in a three-dimensional flow, all three variables and all three velocities come into effect, and this is an example of a three-dimensional flow, the flow around a car, and we will come to this later on. All right, so we talked about the left-hand side being the Naiver Stokes equation, the left-hand side of the equation being the total acceleration of the fluid. And we have x, y, and z components because it's a linear momentum equation, while the right-hand side of the equation is the forces per unit mass. Here, just to summarize, this is our local acceleration, the partial velocity by partial t, So that's your local acceleration. And here is your convective acceleration. So here is your the u partial by partial x plus v partial by partial y plus w partial by partial z is actually the del dot v that we have looked at a couple of, actually more than a couple of slides before. So that is your local derivative, and that's your convective derivative, the del dot v acting on the v. So the v here is my small u, and small u, while this, the summation of those three items is the convective operator, convective derivative. So you need to be familiar with those terms, what we mean by local acceleration, convective acceleration, and the entirety of them is the total acceleration of the fluid. Here is our gravitational force per unit mass, pressure gradient force, as well as the viscous forces. Remember, in our derivation, we had the viscous stresses had two types. We had the shear stresses, so these are the off-diagonal elements, so these guys over here, so these are shear stresses, as well as those three guys over there. These are all shear stresses. And then we had normal stresses that are on the diagonal of this matrix over here. And these actually sum up, these are normal stresses, and we talked about the pressure also being a normal stress in our derivation. But here we're separating them because this is the usual form of the Naiver Stokes equation. So moving on. Now let's look at, we want to get a little bit more feel of this local acceleration and convective acceleration. So here we look at, let's look at two pipes, a pipe of diameter capital D, D inlet, and it's connected through a nozzle or a contraction to a pipe of small diameter D, D exit. So from mass conservation, we know that the velocity will increase from a velocity v at the inlet to v at the exit in proportion to the area ratio, d exit over d inlet squared. Now let us take a small control volume dx dx dy. So this is my x coordinate along this contraction. And what we mean by the local and convective acceleration. If I look, now this window is fixed in space and the flow comes inside it and leaves at a slightly different speed. But if I look at the flow at the center of this cube, I would have local acceleration. So by the flow I mean is the velocity in the x direction, which is my u. If I look at the u signal as a function of time, I would have local acceleration if there is variation of the velocity here with time. So now it would be 2 meters per second, and 2 seconds later it'll be 5 meters per second. And that's what we see here. And if that happens, then I would have a local acceleration, the unsteady term. So that's easy to understand. But now if I plot the u velocity, because as we said, we start with u equal to capital V0 and we exit with u equal to capital VE. And I can plot it here with x, and you'll see here is your V0. You start with V0 and you exit at a velocity V exit. That's the horizontal component of the velocity. And if you notice, if you look at this cube, we have a variation of velocity delta u between the between the inlet and the outlet. My velocity u has changed by an amount of delta u over a distance of delta x. So that's my du by dx. And you multiply that by the velocity at the center of this cube. So that gives you units of acceleration, meter per second square. So that is what we mean by the convective acceleration, is that the variation of velocity in space creates and acceleration. And this is how we quantify it through the gradient, the spatial gradient of the velocity. So that's what we mean by local acceleration and convective acceleration, and what they would mean. So let's have some notes on the Naiver. Let's go and revisit our Naiver Stokes equation and note a few things about them. One is that the Naiver Stokes equation is a nonlinear partial differential equation, and the nonlinearity comes from the convective acceleration. The rest of the terms in the Naiver Stokes equation are linear. It's a second order, primarily because the viscous stresses are second order. And there is no closed form solution. You can Google the Millennium Mathematical Challenge. It's a fun thing to read. So there is no general closed form solution, but in this course we will take some very simple problems, and there are special problems in fluid mechanics, and for those, under certain assumptions, we can find closed form solutions for the Naiver Stokes equation, and that's the goal of this chapter in this course. So now that we have derived the Naiver Stokes equation, which is the equation that describes mass and momentum conservation of any fluid particle that's within my fluid domain. So let's go back to our hairdryer experiment. My fluid domain is inside this box. That's where my fluid is. It's air. It has a density of 1.23 kilogram per meter cube and a viscosity of around 10 to the minus 5 Pascal second. We have our coordinate system. We're dealing with the Cartesian coordinate system. As we said, the Naiver Stokes equation describes the dynamics of the motion of each fluid particle inside our fluid domain. So whether it's from a hairdryer, or the air you're breathing, or the water coming out of your tap, or whatever example you take for a Newtonian fluid. So the first thing we need to do is to supply the geometry. So our geometry, typically we're interested in the ball, because the ping pong ball is our interest. So for here we're considering this as our geometry. It's a decision that you have to make. And then we have the equations that describe the flow. And then we integrate, or first we simplify the Naiver Stokes equation as much as we can, and then we integrate them. That would leave us with some constants of integration. And to get the constants of integration, we need some knowledge on the velocity and pressure at the boundaries, which we call the boundary conditions. So let's now try and consider the ping pong ball, which is what we have over here. This is our ping pong ball, and I've taken this as my fluid domain. My fluid is between the dashed black line and between the ping pong ball. So the boundaries of my control volume are the dashed black lines here. The boundaries of my domain, I should say, and the black line, the black dashed line on the outside. So we've defined our fluid domain, and we've defined the boundaries of our domain. Then we need to know what's going on the boundaries. This information we needed. So just what is coming in. So maybe we know that the flow is uniform at the inlet and it has some velocity profile at the outlet. And we need to know what the pressure is at the boundaries. And then we start integrating the Naiver Stokes equation from the boundaries going towards the center of the domain. And then we can get to the ball and see what pressure and velocity we get over there. And that's what you have done in your partial differential equation course. So let's take a very simple example. So that's the first step. You defined your domain, you've defined your boundaries of the domain, and then you want to simplify the equations of your simplify the Naiver Stokes equation. And let's take the simplest case. Is a static fluid where I don't have a motion in the X, Y, or Z dimension. It's just the water sitting in your water bottle, or in your the coffee sitting in your cup. and it's not moving. So anything in the equations with u, v, or w will be 0. So you'll see all these terms cancel out because you have a u, and all these terms cancel out because you have a u, as well as these terms because they have a velocity v. So that's all 0. So the x component of the Naiver Stokes equation, which is the top one, gives me dp dx equals 0, and the y component gives me dp dy equals 0, and the z component gives me dp dz. So h is z here, is minus g, minus rho g. The x and y components of the pressure don't give me much, but the z component I can integrate. These tell me that the pressure is independent of x and y, while the z component tells me that the pressure varies linearly with z. And then I got a constant of integration from the integration. So now I have to apply my boundary conditions. So at the top of your cup or your glass of water that's sitting on your desk, the pressure would be atmospheric, where you know what the height of your cup is. And then that would give you your constant of integration once you have defined your coordinate system z, your reference z. So you apply your boundary conditions and then you get your solution. Now we are going to talk about different types of boundary conditions. So let me actually pause here for a second, and then because the video is becoming too large, and then we'll move on from there in the next video. So I'll see you in a short bit. Thank you.